of a spring mass system without considering the mass of the spring. In this particular case, we'll be considering the mass of the spring. So I'll be just drawing the spring mass system here. Uh, so this is the support, this is the spring, and this is the mass. Okay, so this block has mass m. Okay, the spring has the length L. Okay, and it has a stiffness K. So here what we will be doing is we'll be assuming m be the mass of the block. Okay, so ms will be m suffix s will be the mass of the spring, mass of the spring. L will be the length of the spring. We'll be using a term called as delta here. Delta should be mass per unit length of the spring. Mass per unit length of the spring. Okay, so in order to do this, we'll be using energy method to solve the problem. Okay, so the energy method, as we all know, that it says that d by dt of kinetic energy plus potential energy should be equal to 0. So this is the formula which we will be using to solve the problem, or this is the equation. So here, if you observe, I'll be giving, as we are trying to find out the natural frequency of the system, I'll be giving the initial displacement to this mass, which will be having a displacement x. Because of this displacement, the spring will be having the potential energy, whereas the mass has the kinetic energy. But in this case, we'll be assuming the mass of the spring. Because of that, we'll be having two kinetic energies. One is kinetic energy of the mass m, and similarly kinetic energy of the mass of the, that is ms. We'll be having both the masses here. So in this case, what we'll be doing is, first we'll be finding out the kinetic energy of the mass m. So we know that kinetic energy of that mass will be half into m into x dot square, because x is the displacement, x dot will be the velocity, so it will be half into m into x dot square. But there is a problem that how to find out the mass of the spring. For that case, what we'll be doing is we will be assuming a small length dy. We'll be assuming a small length dy at a distance of y from the fixed end, at a distance of y from the fixed end. So in that case, what needs to happen is, what is the formula for kinetic energy? It is half into m into velocity square. So I need to find out the velocity of this small element, then I'll be integrating it to get the value of the whole system. For that case, what we'll be doing is, first I'll be writing a linear equation, that is, at this particular point, if you observe, the displacement is x at L is equal to at the distance L, we have a velocity x dot, at a distance L. So what will be the velocity at the distance y? So what will be that? The velocity at distance y will be, cross multiplication if I do, x dot will be y by L. X dot will be y by L. So this will be the formula for the velocity of the spring at a particular distance y. So now I have to write the kinetic energy of this. So as we have assumed a small element, okay, small element, that is dy, for that first we will be writing the kinetic energy. So what will be the kinetic energy for this? This will be half. So I'll be using the term called as delta. Okay, that is mass per unit time, delta into dy, because if you see what is delta here, delta is mass per unit length. If you multiply by length, it will be m. So delta into dy into velocity square, that is x dot into y by l the whole square. Okay, onto whole square. So next, what we'll be doing is, this is the kinetic energy of the spring, of the spring, and if I want to integrate it for whole length, so what I'll be getting, 0 to length L, 0 to length L. So for that case, I'll be putting these terms into that. So kinetic energy of the whole system, kinetic energy of the system will be equal to kinetic energy of mass m plus kinetic energy of the mass ms. Okay, kinetic energy of the mass ms. So in this case, what will happen here is, kinetic energy of the mass m, it will be written as half into m into x dot square, plus what will be the kinetic energy of this small mass ms. So it will be half into integration 0 to l dy, sorry, this will be, this is rho, have to, this will be rho. If I want to write it for total kinetic energy, it will be rho into, give me a second, just rub this out, integration 0 to l rho into dy, okay, into x dot y by l the whole square, x dot y by l the whole square. So what I'll do is, I'll just do the integration of this, half into m into x dot square, okay, half into m into x dot square, plus half, I'll be keeping it outside, I'll be getting it rho also outside, x dot square upon l square also I'll be keeping it. I'll be integrating y with y square with respect to dy. So what you will be getting, y cube by 3, the limit will be 0 to l. So what you will be getting, half into m into x dot square plus half into rho into x dot square upon L square. If I put the limits, it will be L cube by 3. So what you will get, this L square and this L square get cancelled. So what you will be having, you will be having half into m into x dot square plus half. So rho by L, okay, it is rho divided by L. It is nothing but, this is mass per unit length, mass per unit length into uh, mass per unit length into length. It's not rho by L, it is into L. So it will be gets cancelled. Here you will be ending up with term ms. ms into x dot square divided by 3. So what you will be ending up, the kinetic energy, half into m into x dot square plus ms x dot square divided by 6. This is the kinetic energy of the, total kinetic energy of the system. Okay, so what will be the next term? Next term, if I try to understand, potential energy, potential energy of only for the spring, we need to write it. So it will be half into k into x square, half into k into x square. For that case, now if I put the all the terms in the energy equation, that is d by dt, kinetic energy plus potential energy should be equal to 0. So for that case, what I will be doing, d by dt, so what is total kinetic energy? It is half into m into x dot square plus m suffix s x dot square divided by 6. This will be the total kinetic energy, plus potential energy will be half into k x square, should be equal to 0, should be equal to 0. So what you will be getting, so if I do the differentiation of this, so it will be half into m into 2 x dot x double dot, this will be the integration, differentiation, into ms by 6 2 x dot x double dot plus half into k 2x x dot should be equal to 0. So here what happens, 2 gets cancelled, 2 ones are 2 3s are 2 gets cancelled, and x dot being common, this gets cancelled. So what will end up here is, here also x dot gets cancelled. Okay, so what you end up here is mx double dot plus ms by 3 x double dot plus kx should be equal to 0. So if I take x double dot common here, you'll be getting m plus m suffix s divided by 3, okay, plus k into x will be equal to 0. So according to our law, if I make uh, x double dot as a without any coefficient, so what it will become, x double dot plus k upon m plus ms divided by 3 into x will be equal to 0. So from this, what you will be getting, omega n is nothing but square root of k upon m plus ms by 3. So this is the natural frequency of this particular system. Okay, so what we have done, I'll just give the overview of this. Okay, we are interested in finding out the natural frequency of the system by considering the mass of the spring. So these are the nomenclatures which we have used. Okay, but when we write kinetic energy of the whole system, the kinetic energy of the whole system will be consisting of the kinetic energy of the mass of the block as well as the kinetic energy of the spring. So for that case, kinetic energy of the mass is quite easy. It is half m x dot square. But when we are finding out the kinetic energy of the spring, that spring has to be found out. For that, what we did is we took an element dy at a distance y from the fixed point, okay, or the fixed end. So for that case, the equation comes here like this: half into rho into dy x dot by y by l whole square. So this how we found out the velocity. I have told you the logic here. So then when you solve this, you will end up in this particular equation. So this is how we'll be solving the natural frequency of the system considering the spring.